chemical changes?
Right there.
Oh, right at the top. Cool. So physical properties. So these are observable characteristics that do not alter elemental composition. Okay? Said another way, they don't alter the chemical composition. Right away, you should be screaming, wait, what? You're defining a term by using the term that this class is based on. So you've all taken lots of chemistry, so you know what a chemical composition is, right? Yeah, that makes that a bit challenging. Okay? If we move to chemical properties, maybe we get a better definition here. Chemical properties define how a compound changes its bond structure when it interacts with other compounds or elements. Said otherwise, the chemical properties are the things that involve chemistry. Okay, so we just introduced two terms, and with those two terms, defined them using the term that you're supposed to learn this semester. That doesn't really make any sense. Okay? Defining a term by using the term is very cyclic and it doesn't help you. Okay? Problematic. Okay? Until we really understand what's going on with chemical bonds, what makes a bond, that makes classifying physical and chemical properties a little bit more difficult. Okay? So we really just come up with categories that we group based upon, and we just kind of work from there. And as you learn more information, you can start to apply these broader properties a little bit better. The big examples that you might remember or you might know from your physical properties, phase transitions, okay? Liquid, solid, gas, all we're moving is changing that phase. That does not change the chemical properties. The compound stays the same, but we end up changing the physical properties. How fast is it moving? Okay? It's still a ball, it's just moving faster. Okay? That's a physical change because it's still the ball. Kind of, sort of? The other properties that come out of this. Colors. Okay? If we look at a substance and it is blue, that is a physical property. Okay? It has a blue color. Density. Okay? How much of those individual particles exist in an individual volume? Okay? Also a physical property. Solubility. Does it dissolve? Does it mix with something else? Okay? Tends to be a physical property. Conductivity. How do electrons pass through said material? Also a physical property, because the material doesn't change. Something just passes through it. When we move to the chemical properties, what we're doing is changing the arrangement of the components of that compound. Okay? For instance, if I take, let's ignore charges, for any of you that know charges, the element hydrogen and oxygen, and I put it together as just HO or OH. Either way, it doesn't matter. Anybody know what OH is? What's that? It's fine. You don't have to know. You will eventually learn this. Hydroxide? Hydroxide is its name, which you will learn by the end of the semester. What is special about hydroxide? Anybody know anything about hydroxide? Not good is a good answer. It is a very, very strong base. Okay? If you start touching hydroxide, that burns you rather severely, so we avoid touching concentrated hydroxide. But if we go through and change the chemical composition, and now say instead of having just one hydrogen and one oxygen, I switch to now H2O. What do I have now? Water. Do we really care about water? I mean, it is important to our survival, but it's not going to kill us if it touches us. Theoretically. Depends on the amount. Okay? And the state. Okay? So we're changing the chemical properties because we're changing the number of units that go into that individual compound. If we change it yet again, what do we have now? And we got like a cut or something, and somebody pulls out that brown bottle, puts some, it's hydrogen peroxide. Hydrogen peroxide also extremely dangerous. Okay? That's why it hurts when it touches your cuts. Because what is it doing? It's killing everything it touches, okay? Including your open wound. Okay? But theoretically, it's only that small part that's open, so we're not killing that much. All we're doing is killing all the other germs. Okay? We could push this even further. What happens if we change this to now 3 hydrogens and 1 oxygen? Go for it, yeah, strong.
Stronger, right? The hydrogen's
Stronger what? It now becomes an acid. And we now have a really strong acid, also not particularly fun to touch. So by changing the composition, the chemical composition, we change the chemical properties. How does it interact with something else? Okay? In a bond-type fashion. Okay. What do you guys think? Somewhat clear? Sort of clear? Okay, let's make it more interesting. So what observables suggest a chemical change? So if we look at an individual reaction, how do we say, that is a chemical change? Okay, so we've got 3 pictures down at the bottom. What's happening in that first picture? What do you see?
Heat.
Very difficult to see heat, right? Heat is a temperature. It's how do you feel it? We're seeing a phase transition is the broadest sense of this. When we add heat to a substance, we can get a phase transition. By adding that heat, we can force it up into the gas phase. We aren't actually adding heat in this case. What have we added?
Another chemical.
We added another chemical. We took a little silver block, we dropped that in this pot of boiling or pot of water, and all of a sudden gas started coming out. We got a phase transition. Okay? Well, phase transitions, we say, would be a physical change. But that's only a physical change when what? Nope. If I boil water, I can see the water boiling. I get the exact same visual result as this. How do I boil water?
You add heat.
I add heat. What if I add that solid in that water but no heat?
Same thing.
Should I get a phase change?
Yeah.
I should not get a phase change. Why am I getting a phase change? There's energy being supplied somehow outside of a heat source. That energy supplied is chemical energy. There's our chemical reaction. So just because we have a phase change doesn't mean we have a chemical reaction, but it is something that could signify it. So one of the things that we need to look for are we adding heat or potentially removing heat? Because both of those elicit phase changes. If we do not add heat or remove heat, okay, and we get a phase change, the energy required to do that phase change had to come from somewhere. That somewhere is chemical energy, and that's our chemical change. All right? What's happening in the next one? All right, we could look at a vapor. We're seeing flames and sparks coming out of this. Okay. And just as I said, no, we don't see heat here. What am I say we see here? We see heat. Why do you see heat? We're seeing flames and sparks. How do we get flames and sparks?
Heat.
It's usually a sign of heat. Okay. So our reaction, we mix 2 things, and what happens? We're seeing this release of heat. Did I add that heat? Did I remove that heat? No. I mixed 2 things, heat appeared. Where did that heat energy come from?
Interaction between chemicals.
The interaction between chemicals, we had a chemical reaction. Okay? Last one, what's happening? Color change, keep going. How do you know it's turning into a solid?
Well, because you can see from the composition of it. That it
I
looks-
agree, keep going. So we're seeing a phase change here. Okay? And this is kind of an odd one to pick up. We know that there's a phase change because what you have to do is look at your 2 starting materials. Those starting materials have what property?
They're both liquid.
They are both liquid and they are both, yeah, that's a fancy way of saying it, clear. They're both clear liquids. What happens when we mix those 2 clear liquids? It becomes not clear. What phase typically is not clear? Solids. Why is light no longer passing through? Solid is forming. Okay. Specifying the color change is a little bit of an odd one. I won't necessarily say it's wrong, but it can be kind of tricky. Okay, you're saying there's a color change here. Really? It started yellow.
Was it dark
Okay? So you can run on the intensity of the color, but we'll still run into exceptions on that. Okay? So as a general rule, we can come up with three main classes or three main observables to decide is it a chemical or physical change. Okay? So your chemical changes, typically phase changes without heat, change in temperature without adding heat or removing heat on our part. We mix two things and we let it do its own. Does the temperature change? And then a permanent color change. Okay, is the other big one. Okay? What's that? The one in the middle is a change in temperature. It's also releasing gas, but you can't see it as cleanly because you're looking at it from the top.
Can they do that with hair color?
Hair color can be both both chemical and a physical change, actually. So, since you guys now, or wait, actually, before we do that. So clear as mud? Everybody understand chemical and physical changes? Okay, guess what? Figure it out. Talk to each other, see what you can come up with. We've got 1, 2, 3, 4, 6 different things up here, which I will now color code. What I want you to do is talk amongst each other, figure out what you think each of these things is. Is it chemical? Is it physical? Okay. Or are you just like, I have no idea, that's way too confusing to figure it out. Top, right? And at one end of that rainbow I put the word chemical. The other end of that rainbow I put physical.
Oh, wow.
Yes, what is potentially going to happen here? In our previous conversation, what's happening? We say it's chemical or it's physical. It's black and white.
But it's not.
It is not
The green.
black and white.
The green's in
Okay.
there.
You are looking at a full-on spectrum. At one end of that spectrum, we have purple, which we're calling chemical. The other end of that spectrum, we have red, that we're calling physical. Okay. All of our processes fall on this spectrum somewhere. If it is now a blue color, you would say what process happened, chemical or physical?
Chemical.
Chemical. What if I said green?
Anything.
It's right in that gray area. It's a little difficult to classify as a chemical or physical. That's one of the reasons why this process or this kind of assignment makes it difficult to understand. Okay? And depending on how much you know, you may classify something differently. Okay? Which is going to become an important part with at least two of these. So let's start. Melting ice. Chemical or physical? This one is purely physical. Okay? Very far on the physical end. We are looking at a phase transition from solid to liquid, and that phase transition is occurring because I've added heat. I've added energy to that system. Okay? That's what's causing the ice to melt. We're looking at a physical change. Dissolving sugar. Okay? We're running into I heard at least one person say chemical. This one is almost exclusively a physical change. We do not change the chemical composition of the sugar by adding it to water. All we've done is we've taken each of the individual sugar groups and we've separated them away from each other so they're now separated by water. We've got it dissolved. Okay? So we're looking at more of a physical line, but it's a little bit more chemical-ish than our melting ice. So we'll slide it a little bit more towards our chemical side. Burning wood.
Chemical.
Okay, this one is very much a chemical reaction. Okay. One thought that may come out is you're like, well, but I added heat. Okay. Be a little bit careful on that. Sometimes to get a reaction started, we have to add a spark to get it to go. Okay. Once it's now going, are you constantly adding that heat? No. What are we doing, in fact, with that fire? We're actually we're using that heat somewhere else. Okay? That burning of the wood is actually releasing massive amounts of heat energy on its own. Okay? We are looking at a chemical reaction in that case. I'm going to skip dissolving salt for the moment. Mixing red food dye with white cake frosting. This is almost exclusively a physical process as well. Right? It's more like a dilution than anything else. We're adding a deep red color to white cake frosting, and now our cake frosting comes out a pinkish reddish color. But isn't that a color change? And we even run into a weird gray area on that. What that was a dilution of the color of the food dye. Okay? All we did was just physically put these two things near each other, and that was it. Okay? No chemical bonds exchanged in that mixing process. Okay? Which brings us to the next fun one, dissolving salt. Describe salt for me. And don't tell me it tastes salty. That defeats the purpose.
Sodium chloride.
So we could go sodium chloride. I want even more so.
Coarse.
Describe salt.
It's coarse. It's coarse.
Okay, we could say coarse. Keep going.
Solid.
It's a solid. Yes. Keep going.
Crystallized.
Crystalline. Yeah. Give me a little bit
Absorbs
more.
moisture.
Yeah. We can even absorb moisture. What does it look like?
White.
Thank you. We have a white solid in salt. Guess what I'm going to ask you to describe now? Sugar. Describe sugar for me.
White.
A white solid. When we dissolve sugar, what are we doing? We're taking a white solid and we add it to water, and we see it dissolve. We see the solid disappear. And dissolving salt, what do? We take a white solid, and we add it to water, and we see the exact same result. What type of reaction is dissolving salt? Chemical or physical? Right? We're getting a lot of gray area in here. Why? Okay. Anybody? Well, we already addressed this. The formula for salt, sodium chloride. Anybody know the formula for sugar? Good, I was right earlier this weekend. C6H6. What happens when we dissolve sugar? Okay, we start with C6H6 and we know it's a solid. How can I specify that it's a solid with this equation? Solid's too many letters. We put a parentheses and just say S. Okay? We now have a solid. What happens when I add water? I get C6H6. Nothing changes to the formula, but how do I know it is no longer a solid? I change the phase to now say AQ. It's now no longer a solid. What does AQ mean? Aqueous. Everybody says aqueous. Aqueous, doesn't really matter. Same thing. Potato, potato. What does that mean? It is now dissolved in water. Sodium chloride. You specify that it's a solid. What happens when we dissolve it in water?
Sodium and
We separate the sodium from the chloride. Okay. What happened to the chemical nature now of sodium chloride? It is different. Its chemical nature has changed, which means chemical. Okay. We could add the extra information that these are both dissolved in water by adding the AQ, but in this case it really doesn't matter because we've already specified that those atoms have separated from each other. Okay. Why is this a gray area? Well, what we just talked about on what we physically observed was that we got the exact same result. So according to our physical observations, we would say physical. According to looking at the actual chemistry that's occurring, we say it's chemical. When we're looking at sodium chloride, it falls almost perfectly dead center between these. And depending on who you talk to, you will get a different answer. Okay? On is it chemical or is it physical? Because they've been divided into the two camps of it's either chemical or it's physical and there's no other in between. It's not true. There is a very large in-between area. Okay, so now the question becomes, exam question. Multiple choice, which of these is chemical? would you expect to see dissolving salt? Okay, why would you expect to see dissolving salt? I'm interested to hear the answer to this.
I don't know, A could be chemical, B could be physical, and C could be...
How many of you understood that sodium chloride dissociated into sodium ions and chloride ions before we just addressed this issue? One person. Huh. 2 people? 3 people? Huh. Well, that's fun. So I just put a test question on that only 3 people in the entire class can answer. That's less than 10% of the class has a remote opportunity to getting the answer right. Okay. This is why I wanted to hear why you thought I would put it on the test. Okay. I wouldn't put this question on the test. What I would put on the test are the extreme circumstances. What is strictly physical? What is strictly chemical? Okay. You would not see these gray area options. If they do show up, what could you do? There were a couple answers. Let's hear, I think I heard someone here first, then we'll go over here. So. No? Was I wrong? I'll go over this direction.
They could argue that it's like both either chemical or...
Who are you arguing with?
You.
Talk to me. Okay. Theoretically, you could even talk to me during the exam. You read the question, and I'm like, whoa, he said this was a bad question. Raise your hand. I'll come talk to you, and you'll be like, you said this was a bad question. I'll be like, yeah, you're right. I did say it was a bad question. I'll just remove it from the exam. Okay. If you ever come up with a situation where you're in a gray area, ask. Okay. Gray areas do pop up. You got to ask. If you don't ask, then I never find out that a mistake was made. You never get credit for the points. Is that a question? Okay. Bree?
So, is this Scantron a question is what you're asking? So, because you could...
Most of these are
otherwise.
Scantron. Yeah. Most of your questions are Scantron.
Because that would...
In a short answer format, I could still ask the question. I could say, is dissolving salt chemical or physical? Ooh, bad question, because it's now true or false. It's either chemical or physical. How do I fix that?
Answer both.
Explain your answer. If you answer chemical, what should your explanation tell me? Sodium chloride separates into sodium ion and chloride ion.
Right.
If you tell me physical, what's your explanation for physical? It just dissolves. I started with solid, and it just became aqueous sodium chloride. Okay. So your explanation can change your answer. Okay. Questions on that? Last one's another fun one. It gets into color changes. This was an experiment I tried to do for my organic chemistry students, and it's failed every time I've tried it. So I'm going to stop doing it. Okay, we make this molecule, this crystal structure. Okay, what color is that? Looks yellowish. People up here can help people in back. Okay, yellowish. Okay, what they're not showing here is that what we've done with that crystal is shined a light on it. What happens over time as we shine the light on it? It gets darker. It turns into this kind of purple crystal. Kind of a neat color change. Chemical or physical? It turns out to be chemical. That compound will change its chemical structure when it interacts with light. Have you seen this before? There's a few people that have glasses, so you may know. Your transition lenses are this chemical. Okay. There is a chemical reaction happening in transition lenses. When you walk outside, there's ultraviolet light. That's why we put on sunscreen, all that fun stuff. That ultraviolet light hits the lenses, causes the chemical change. It gets darker. Okay. So they vary the amount of that compound in the lens to get really, really dark so you couldn't see anything, okay, or gray areas in between. Okay. Where else could you have seen this if you were significantly older, say alive and remembering things in the late 80s, early 90s? What's that? Someone have it? No, not photos. That's actually a different process. This is a reversible process. Photos is not reversible. Anybody remember those color-changing T-shirts? Yeah, your hypercolor T-shirts. Yeah, they stopped making those. As you might guess, if I was wearing one, you would notice some very kind of awkward color changes. Anybody know where those awkward color changes would be? My armpits would be a very brightly different color than the rest of the shirt. They kind of decided that was a bit odd, and so they stopped making them. Okay.
That's like when you DJ and you use an ultraviolet light, and all of a sudden it
Yeah.
makes everything see-through.
Yeah.
That's always
Okay. Questions on your chemical and physical? Okay. So, there's nothing over there. Law of conservation of energy. Okay, just like matter, energy cannot be created or destroyed. So we can convert from one form into another. We already started talking about energy unintentionally because I thought we'd already talked about it. My bad. There are 6 forms of energy. What are those 6 forms? Heat, electricity, light.
sound.
Sound isn't classified on this, at least as sound.
Heat.
Magnetic also, interestingly, isn't classified on this. What was that?
Heat.
Heat's already on our list. Nuclear. Mechanical. I'm running out of hands.
Potential?
Kinetic and potential are forms of mechanical energy. What class was this? Chemical. Okay. We have chemical energy. So we've got all of these different forms of energy. We can convert between them, okay, but we cannot create or destroy them. Okay? For instance, we stuck a finger into the electrical outlet. Don't recommend it. Don't do that. Okay? We get zapped with electrical energy. What is that electrical energy being harnessed to do? Power something. What do you mean by power something? We're going to convert that electrical energy to do something else for us, say like light. What we are doing is pumping that electrical energy into a tube, and it's actually an interesting process because it's not just going into light. We pump that electrical energy into atoms, right? And we make some chemical energy. That chemical energy gets released in the form of light energy. So just our process of powering our lights here, we go through several sequences of energy changes. Right? The ultimate kind of end for all energy is heat, okay, which is bad. Okay? If you're an engineer, heat is something you're always trying to limit because we can't control the heat energy as efficiently as any of the others. So when we look at mechanical energy, we get this idea of potential and kinetic energy. Potential energy is how much energy is stored, okay, without motion. So if I took a cannonball and just balanced it maybe an inch above my head, there's not very much potential energy. But if I move that now 6 stories above my head, I might have a little bit more fear of the potential energy in that cannonball. Okay? The kinetic energy is now how that potential energy gets released, so that when I let go of that cannonball, all of that potential energy as it falls is now converted out of potential energy and into kinetic energy, which is now the motion of the cannonball. And ultimately, I'm afraid of that now very highly kinetic energy cannonball all suddenly losing or transferring its energy into my head. Okay? So we want to avoid that if at all possible. There are other examples of where we're looking at fun mechanical energy. How did you all get here? In a car. What's a car doing? Moving via mechanical energy. Where did it get that mechanical energy from?
Chemical.
Your gas, which was a chemical. What are we doing? We run a chemical reaction, which is converted based on our combustion engine, okay, into a couple things. Number one, heat, but more importantly, it's turned into mechanical energy that allows our car to move forward. Okay? That heat energy is our big loss, because we aren't using that heat to cause the car to move. What we're using is the pistons moving to cause our car to move. So what we want to do is minimize that heat as much as possible. So there's a sizable amount of research in the combustion engine on trying to minimize heat production and dissipation through the system, because that heat energy messes with everything else. Okay? How else did you all get here? Because I'm pretty sure you didn't drive into this classroom. You walked. How did you walk? You used chemical energy in the form of ATP, or adenosine triphosphate. ATP in your body gets converted into ADP. And that's all they tell you in biology. You go, man, there was energy. Guess what's happening in that form of energy? You are simply removing that last phosphorus and oxygens. That bond has such high chemical energy that when we cleave that off, we can harvest that energy and use it to power our muscles.
Triple to double.
Yep. Adenosine tri for 3. Adenosine di for 2. So 3 to 2. Okay. Kind of a neat process. We're getting all of that energy from somewhere, and ultimately, as far as we're concerned, it's all coming from chemistry. Because we're chemists and we're selfish, egotistical people. How can we manipulate this back to our phases? Right? So we've got 3 boxes here. What do those 3 boxes represent? Solids, liquids, and gases. How do you know that? Okay. Remember, we talked about on whatever that last day was, Thursday, about what different properties we got out of solids, liquids, and gases. We could look at compressibility. We could look at all those other features. If we look at compressibility, what did we say happened with a solid? Could we compress it? No, why not? There's no space in between the atoms to compress. So we've got a solid. How about the next one? It's a liquid. Can we compress the liquid? A little bit, but not much. And then we have, I can't spell liquid, son of a... Really what I mean is I can't spell it uppercase, which I don't know. And the last one we have, gas. You'll notice I can spell gas and solid uppercase. I can't spell liquid uppercase. So, how do we tie this back to our energy? Which of those phases has the most kinetic energy? Gas. Kinetic energy was our measure of motion. How much is it moving? Well, if we put a solid on the table, what happens to the solid? It stays there. It has no kinetic energy. If we put a liquid on the table, what happens? It moves to fill over whatever shaped container is holding it. In this case, it would just spill onto the floor. Right? If we try to put a gas on the table, what happens? It immediately moves to fill the whole room. Right? Our gas has the most kinetic energy. Okay? So those simple observables that we came up with before on compressibility, shape, okay, and the other one, whatever the other one was, all can come back to looking at our individual phases according to their energies. Okay? Do all phases have kinetic energy? Yes. Every single phase has atoms in it, or units. Each of those units is constantly moving. In the case of a solid, that movement happens to be very, very small that we don't detect it and we assume that it's nothing. Okay? But it is still moving. When we move to gases, we've got what? More or less kinetic energy? More, because it's moving a lot more. So remember, kinetic energy, for all intents and purposes, is just motion. So if we've got a gas, we've got a lot more motion. Okay? What happens when we increase the temperature? The kinetic energy increases. What happens if we decrease the temperature? The opposite. Kinetic energy decreases. Does that match to what we understand for our phase changes? What happens when we add energy to our solid? It becomes a liquid. What happened to the kinetic energy when we compared liquids and solids? Liquids had more. What happens if we add more energy? It goes up to a gas. What happened to our kinetic energy? It goes up even further. Okay, so it matches all of those standard descriptions. Are there other phases? Yes, but let's pretend to ignore those. Okay? Those are the ones we only need to be concerned about. Energy and chemical changes. Okay, so when we're looking at a chemical reaction, we can convert our energy into different forms. So for instance, we could start with water and we could pump electrical energy into it. In that process, I can force a chemical change. In this case, I'm forcing that chemical change to separate water into its 2 components, hydrogen and oxygen. Why might I want to do that? We mean burn it. What are we burning?
The hydrogen and
Burning the hydrogen. Or the hydrogen fuel cars. That's what they're trying to do. Okay, so what we then do is now have the hydrogen with the oxygen. We burn it. Same deal as the combustion energy, except our product in that case ends up being water. So we look at it, oh, I've got a car that now moves on super clean energy. Phenomenal, fantastic, saves the earth. Why have we not seen more hydrogen fuel cars?
Because it's extremely dangerous.
We do have some danger with the hydrogen, but it's actually not that big of a deal. If that was it, we'd actually move beyond it.
batteries and efficiency.
Even batteries aren't going to be a big deal because we have a fuel. It's the hydrogen. And it is something to do with efficiency.
So like implementation.
Not even the water.
Is it the heat?
Our whole point is to remove CO2, so we stop producing CO2. How did we get our hydrogen? Where did the hydrogen come from? It came from this reaction, which came from pumping electrical energy into water. So this second reaction for our car, beautiful, amazingly clean, readily available oxygen, and we've now supplied a bunch of hydrogen gas. The hydrogen gas came from adding water and electrical energy. Where did our electrical energy come from? Coal, which is as dirty, if not more dirty, than gasoline. So yes, we cleaned up the car itself, but how did we get energy into the car? We did it by making an even bigger mess. That kind of defeats the purpose of moving to that technology. So until we can come up with a cleaner source for electrical energy, the combustion engine isn't really going anywhere. Okay? Kind of neat process. You got to look at every stage of that chemical system. Okay? Questions? Okay, let's switch to gas. Gas is always fun. You may have heard this in terms of expense. Okay? How much is this going to hurt your pocket? Is it better to fill a gas tank in the cool morning or the warm afternoon? I'll give you a hint with the liquid and the gas. Why in the cool morning? You could see some evaporation, but theoretically we got that cup on the gas thing to keep everything, all the gas in the tank. So evaporation isn't going to be that big of a deal. Less heat, less movement. What does that ultimately do? It makes your gasoline denser, which means when you measure out your individual gas to the tank, you're not paying for the number of chemical molecules, you are paying for the volume of them. If we change the density of the chemical molecules to be a very low density, you don't get any gas molecules out of it, which means you have to buy gas a whole lot more. Okay? So if it's really cold, your gasoline now becomes closer towards a solid, less compressibility. You get more molecules per individual area. Then if it was hot and we start equating to the gas, we get very few gas molecules in that individual area. So it actually makes sense to fill up your car when it's cold as opposed to when it's hot. How much of a difference does that make? Like fractions of a penny on a gas tank. Like the whole gas tank.
Really?
Fractions of a penny.
That's all it is.
Okay. So it really
That little
doesn't
bit.
save you much. I wouldn't worry about it. Why? Why does it not save you much? They come up with other things. Are we pushing to the gas with the heat? When you fill up your car, are you filling it up with gasoline, or are you filling it up with liquid gasoline?
Liquid.
Are you filling it up with solid gasoline or liquid gasoline? Liquid. So we're only looking at the liquid phase. What was the compressibility of the liquid? Not very much. So even when you change the temperature, your compressibility doesn't change much. You're not looking at much of a difference. Yep, pretty much. With some basis in science, which makes it even more dangerous. Other questions? You were going to add something else?
I was just going to say, most of the gas pumps in different parts of the world, I don't know about here in particular, they auto-correct the temperature. Not auto-correct, but they have...
Oh, that's interesting. I hadn't heard that.
The gas is actually set to a certain temperature so that no matter what time of day or year, if it's minus 20 outside or 150...
It's going to dispense the same amount.
the same.
That's cool. I had not heard that. You know whose idea that probably was? Just to sort of plug my political systems. It was probably the government. Because I guarantee you, the gas company was not creating a system to say, oh, we'll make sure we dispense the same amount of gas. They were saying we'll dispense as little as possible. But that's neither here nor there. Conservation of mass and energy. Okay? Einstein came along and actually came up with an equation or the physics behind it to relate mass and energy. So if we can't create or destroy mass, what can we also not create or destroy? Energy. Okay? That is written out in his famous equation. E for energy equals, you can't participate anymore because you already know the answer. Mass, okay, you can't participate anymore. C, speed of light. Okay, cool, that worked pretty well. You guys can start participating again. Okay? Yeah, that's about all I got to say on that. You could run some calculations with that if you really wanted, but not that big of a deal. Oh, look at that, a quiz. Well, we'll now move into, we started at 30, so we're done at 45, right? Okay. We'll now move into is the PSS chapter, which is the, I don't even know what the textbook calls it. For some reason, as they moved from the 6th to the 7th edition, what they do is took a section out of chapter 2 and made it a whole new chapter. Why? I think I may have heard it. Money? Yeah, that's a good answer. Okay. They can't sell the same textbook for 2 or 3 years because then people start buying the used editions and they stop making money. So what they do is every 2 or 3 years, they update the textbook so that now nothing matches. Now everybody has to buy the new textbook. And they wait another 2 or 3 years, and then guess what? They update the textbook. Okay? So, consistent across all classes, particularly science classes. So on almost all of your classes that you take in the future, you might very well be able to buy the next or the most recent older edition, and you're probably fine. Right? Can save you probably $200 to $300.
Yeah, I got mine for $10.
Okay. Yeah, they're due to update, which is why we're due to not use the textbook anymore. So in this chapter, we've got a couple things that they're talking about. Types of measurements, significant digits, which you will learn to hate or love, depending on your opinion. Carrying sig figs, so once we know what our significant digits are, how do we use them and manipulate them, and then some scientific notation stuff. Measurements. Okay. All numbers in this class are wrong. Okay. Can't stress that enough. Every single number in this class is wrong. Okay. What would make that number correct? A unit. If you write any number down and there's no unit attached to it, that number is wrong. Okay? It has zero meaning. In a science class, you must have units. Okay? Every number carries a unit. We've got 4 things that we could observe or measure or quantify. We've got distance or length, which is typically measured in what units? Meters tends to be the unit that we use, in the scientific lingo at least, but you got inches and feet that could potentially show up. Okay, one of the things you'll find is not only are scientists egotistical, but they're also lazy. Meters is way too many letters. Lowercase m. Okay. Mass or weight. Okay, these are 2 inherently different things. Mass is a constant, not dependent on gravity. Weight is dependent on gravity. Your weight will change when you go to space. Your mass does not. Okay? What unit do we use for mass? Grams, okay. So either the people that are used to the American system aren't volunteering, or everybody's happy with our science units. What unit do we use for grams? G. Volume? Liters, which gets us capital L. And time? Seconds. We'd also have hours, days, minutes, all those other fun things. Seconds tends to be the scale that's most useful for us. But depending on what we're looking at, we may shift to other units. Okay. So those are our primary units. Okay. We'll make some quick adjustments to this. Okay. We're going to measure a pencil. Okay, so I want to know the length of a pencil. If meters are how I'm measuring, it's roughly 3 feet. What is the length of my pencil? Okay. Doesn't really make sense to use a meter unit because I'm using a very small amount, a fractional amount of meters, and everybody hates fractions. So we end up using smaller versions of some of these units. Grams tends to hold pretty true. Liters, if we walked into the lab and you had to mix a liter of chemicals for each of your experiments, number one, that's a lot of waste. And number two, if those are toxic chemicals, we now just gave you enough to probably really, really hurt yourself or others. Okay? So we scaled down out of the liter unit into milliliters. Seconds is probably fine. So the units that we use most frequently, you'll see milliliters, lowercase m, and liter. And we'll use probably centimeters for our distance. Okay? We've got all sorts of standards. Okay, so that's one of the things that's kind of confusing when it comes to these measurements, is you think, well, meters are defined as something. Okay, well, it was defined. Who defined it? Some guy. Okay? Literally, some guy sat down and said, this is a meter. Somebody else came up and said, no, that's not a meter. And he hit them over the head and they're dead, and now we're still stuck with a meter. It is as basic as that. Okay? These are things that we established as humans and said, this is how we are monitoring it. Okay? And we picked systems that allowed us to monitor because of their ease of manipulation or their ease of conversions between these. Okay? In some cases, they got into a sword fight with each other and nobody died, so they all went off into their separate little kingdoms and they used their own independent units, which is why we have the metric system and we have the commonly known inferior, American system, where we're looking at different measurements for distance. Okay? So we get inches, feet, and all of that fun stuff. Okay? So be aware, you are going to be expected to convert between all of those because somebody wasn't strong enough to kill somebody else. Okay? Unfortunate, but that's the way it works. Or fortunate, I guess. Most of our sciences are based in the metric system. That's where we'll keep most of our focus. So, what is the length of this pretend metal rod? Okay, so interestingly enough, in everything that's been shouted out, I'm hearing a 4-point something. Good. Okay. When we go through to make this measurement, we're going to write down all of the numbers associated with this and our unit. Okay, so in this case, we're looking for an obvious digit. What was that obvious digit?
4.
4. Okay, and I'm going to add one more thing here. So we could say our measurement is 4. We know that to be true. Nobody said 3, nobody said 5. That is absolutely true. But then we said point, and we heard a bunch of other numbers come out of there. Those are guess digits. You always include a guess digit. Otherwise, you are removing that information from your measurement. How many guess digits? 1, and only 1. So in this case, we might look at this and we'd say it's 4.2. I heard a couple 4.3s. Well, whose answer is right?
Mine.
Whoever carries the bigger stick. Okay? We at least came up with some approximation on this, and what we've adjusted to in science is we said there is an error associated with this. I noticed nobody said 4.9. Well, 4.9 is outside of the error of this measurement. So every time we write a measurement, we should also include the error in that measurement. And we would say it's plus or minus. Okay. Why not plus or minus 1?
Because then it'd be 5.
Because that takes us way outside of our limits. So usually we're looking at plus or minus 1 of our last place. So in this case, it's 0.2. It's plus or minus 0.1. Okay? Depending on the measurement, you may see those errors change. Ultimately, all those are is someone took this ruler and that rod, talked to 1,000 people and said, tell me how long this rod is. They averaged all those values and looked at how far off everybody's measurement was. Okay? If their measurement fell on average within 0.1, there's your error. Okay? So the error in your measurement should always be reported with it. When is the first and last time you will report measurements or errors with your measurements? Probably right now. Okay? I don't think we do another experiment where you actually report the measurement. I think that one actually got pulled. Maybe it's the next lab. Okay? If you reported this, you would still be wrong. Why? No unit. So we would then also specify our unit, which I covered up, but it was centimeters. What happens if I change the ruler? Now how long is that rod? Yeah, it's still in centimeters. So we're still at 4. If we look at that zoom in, that's our 0.5. We're looking at 4.2 as a guaranteed. And now we have a guess digit. 5, I'm okay with that. Plus or minus 0.01, why not? Centimeters. Okay? Make sense? Theoretically, always report the uncertainty. And again, you probably never will. Mass measurements, we got these things called balances. I have a colleague that hates it when people refer to them as scales. Because a scale, what has scales? Fish have scales. We use balances. Right. What we're doing is we are comparing to an internal standard the mass on top to some internal standard mass, okay, in the digital ones. In the old-fashioned ones, we've decided on what our mass was, what thing makes a gram. Remember, that was something we defined. So we took a substance and said, this is a gram. We now put it on our balance. We say, okay, does it balance out? Okay, now this is also a gram. Kind of, sort of. Volume measurements. We've got a variety of ways to measure volumes. I guess the other thing we could do is, what do we typically measure with masses? What phase? Solids. Volumes. Jeez. We typically measure liquids. We can also get gases measured with volumes as well. Theoretically, we could measure solids. It's just not quite as easy because solids tend to be irregularly shaped. Variety of different instruments that allow us to measure those. Depending on our units, we'll scale to different things. Okay? So this is really where I want to get into because it makes things more interesting. Significant digits. Okay? When we're looking at a calculation, we need to understand something about the digits that are significant to our number. Okay? If we're using the measurement, we already know the sig figs because we took the measurement. We wrote down those numbers. We know it. But what if we didn't take the measurement? Well, now we have to be able to interpret what somebody else wrote and come up with what they're saying are the significant digits. Okay? So it gives us an understanding of the uncertainty of our measurement. Without understanding significant digits, we can't understand our uncertainty or our error. Okay, so what makes a digit significant? Okay, so if we've got all those numbers down at the bottom, what we want to do is classify each of those according to how many significant digits are in each of those numbers. Okay, and we'll attempt to do this as group work here. Significant digits in the first number. Second number. Third number. Fourth. Last. Okay. Those of you that didn't say anything, do those sequence of numbers make sense? You say yes, then I'm just going to skip it and we're going to move way on. Okay, so no, thank you, I appreciate that. Okay? No, okay, it may not make perfect sense. Someone that has worked with calculations enough, okay, and real calculations, not mathematic calculations, are probably okay with understanding the sig figs. Most of us, not so much. Okay? So what makes a digit significant? First rule, any digit 1 through 9 is significant every single time. No questions asked. So if we look at that first sequence, we could go through and underline our significant digits. That 1 is significant. The next one is significant. 3, 2, and 1. Well, 0, was that significant in our first number? Whoops, I don't know why I wrote 0 there. That was a bit silly. We only have one significant digit in that first number. In the second number, we have 2. So I went from 0 being significant to, or insignificant to now being significant. Why? Decimal is sort of the answer. It actually has to do with what the meaning of the 0 is. Okay? And that meaning is based off of the decimal, which allows us to kind of interpret. Okay? 0 carries 2 meanings. What are those 2 meanings? It's a placeholder. So in the first case, the 0 is there to tell us that the 1 is located in the tens position, which means the value of that number is 10. What if I removed the 0? Now it's assumed to go into the ones position, and the value of that number is 1. So the 0 is there only as a placeholder. Make sure we put the 1 in the proper space. When we move to the next number, what's happened? The 0 is actually holding a value in this case. It's not a placeholder. It is holding the value of not 1 through 9. What is the difference between the number 0 and the placeholder 0? There is no visual difference between it. We have to have rules that allow us to understand when it is meaning what in what circumstances. The difference that pops up here is that we're seeing the location of the decimal point. That decimal point is going to center on what allows our 0 to be a significant digit versus a placeholder. Okay, so here's our rules. If there is no decimal point, then the 0 must be controlled by significant digits or numbers to the left and right at any place. Anywhere to the left, anywhere to the right, it must have a significant digit. If there are significant digits both to the left and right, that 0 is now actually holding meaning as not 1 through 9. That makes it a significant digit. Okay. If it is not controlled by numbers, it's now holding no meaning. It is only a placeholder. Rule 3. If there is a decimal point, then the 0 needs to be immediately preceded, so it needs to be in front of it, by a significant digit to make it significant. If there is no significant digit in front of it, the 0 is a placeholder, and that is it. So, first number. Okay, at least when starting, it can be helpful to underline our significant digits. What could we underline? 1 and 2. Let's avoid the 0 for the moment. That gets us further into our rules. So we'll start with our easy ones, Rule 1. Rule 2, if there is no decimal point, then the 0 must be controlled by numbers to the left and right. What is to the left? A 1. Is that a significant digit? Yes. To the right?
Yes.
Also a significant digit, which means 0 is significant, and I have 3 sig figs. Remember that whole abbreviation lazy thing? Sig fig, SF. And it was even further lazy because it's not even sig fig, it's significant figures. You can see the scaling of laziness. Okay. The next number. What digits are significant? 1 and 2. Do we have a decimal point? No. So that 0 must be controlled both to the left and to the right by a significant digit. Look to the left of the 0. 2. Is that significant? Yes. Look to the right. Nothing. Is that 0 significant? No. It is a placeholder. We only have 2 sig figs. Next one. 1 and 2. What's the deal with the 0? There's a decimal. New rule. Number 3. If there's a decimal point, then the 0 needs to be immediately preceded by a significant digit. So to the left of that 0, what do I have to see? A significant digit. Do I have that? What does that mean? 0 is significant. 3 sig figs. Last number. What's to the left of the 0? Is that significant? Which means underline that 0 because it is now a significant digit. To the left of the next 0. I see a 0. Is that one significant? Yeah, I just underlined it as being a significant digit, which means also underlined. We have 4 sig figs. Do those last 4 on your own here in the last minute of class, and I'll write the answers up here in just a second. If you got a question, you can raise your hand and you can ask that question. But we're pretty much done.